Alright, thanks for watching, and today I would like to talk to you about a really new cool integral that is even more powerful than the Riemann integral or the Lebesgue integral. It's what's called the gauge integral, or also called the Kurzweil Henstock integral or the Denjoy integral. It's all the same thing, and the reason it's cool is because there's some functions that are not Lebesgue integrable, but that are gauge integrable. So it's really cool. For example, like this function, you can show that the integral of this, let's say, I don't know, from 0 to 1, this integral doesn't really exist, neither in the Riemann integral sense, nor in the Lebesgue integral sense. Okay? So this function, the integral does not exist, and because what happens is that this function has a really bad singularity at 0. It just oscillates like crazy at 0. And what's the idea of the gauge integral? We're like, well, if this has a singularity, let's just ignore it. Let's just focus on what's happening anywhere else. And this should remind you a lot of this Cauchy principal value integral, of which I have some other video at some point. And what this gauge integral says, well, if this is a singularity, let's just evaluate the integral from here to here and maybe take a limit of that. So that's the main point. And I'll talk about this at the end if you want. But let me now define this. And the definition is almost identical to the Riemann integral. So suppose you have an interval AB and divide this up into subintervals, which here are just UIs. So this is U0, and then we have U1, U2, up to UN. And in Riemann integration, at least in calculus, those intervals have the same length, like b minus a over n. But in analysis, you learn, well, they don't always have to be the same length as long as they're very small. For gauge integrals, it actually doesn't matter. The lengths don't have to be uniformly small. So you can have something like this, U0, U1, and then U2, U3, tiny, and then up to UN. And the idea is basically, if you're at the singularity, make it tiny so that you don't have, so that we don't really care too much about the singularity. But if a function is smooth, then you can just choose a big interval because the function is precisely smooth. And so, in Riemann integration, and in some sense Lebesgue integration, we divide up A, B into subintervals. But what's important is that for the gauge integral, we choose not only the mesh, but already the points inside them. So suppose you have a mesh and you have a bunch of points. So let's say T1, T2, T3, and they don't have to be uniform. They could just be a point in that interval. Okay. And suppose I give you U and T. Then what you can do is to define the gauge sum, which is just like the Riemann sum. You just evaluate f at the Ti's, and you multiply it by the length of your mesh. So U0, U1. So given UI and Ti. So this is the main difference between the Riemann integral and this integral, because in the Riemann integral, you fix your mesh, and then you choose your points. They're arbitrary. Here, you kind of choose them both at the same time. So given UI and Ti, define the gauge sum, sum g of f, to just be the sum from 1 to n. You sample f at your points, f of Ti, and the length of your mesh, which might not be uniform. So its UI is just UI minus 4. So just here u1 minus u0, u2 minus u1, etc., etc. And as I said, for the Riemann integral, or at least in calculus, you just choose that mesh to have the same length. The big difference is that here we kind of give more leeway or more tolerance to the length of each size, and we do this using what's called a gauge function. So let delta, not like it's an epsilon delta, here it's a function. Think of it as a tolerance, and it's a function from your interval to, I guess, 0, infinity. I guess maybe strictly bigger, yeah. So delta is positive, and that's what's called a gauge, or just think a tolerance. And what this says, basically, it says whenever you have a singularity, be more flexible. The function is already having a bad time, and you want to be nicer to that function. Like here what we want delta to be very relaxed at 0, and usually what the gauge looks like is, again, near a singularity, I think it's big, either big or small, I don't remember. It's big, and then sometimes when you see the function it's smooth, you choose it smaller, etc., etc. So any, I think, it doesn't have to be continuous, so that's an important thing. So just any function from AB that's positive, and then we would like to just rule out bad partitions. So just as in Riemann integrals, you want to rule out big partitions. Here, you want to sort of choose small partitions, but in a very different sense. Namely, given this tolerance, you say a partition is delta fine, so it's fine, but not fine as in good. It means it's small. Before we just said, let n be very big, then our partition is very small, but here it really means it's gauge fine if we have the following. If basically, and again, remember that we fix the ui's and the ti's at the same time. If basically, if you have here ui minus 1 and ui, then if you consider the ball centered at ti and radius delta ti, it has to contain our interval ui minus 1 and ui. And very important, I probably said that 10,000 times that it's important, but it is important. You see, delta is a tolerance. So sometimes it could be big, sometimes it could be small. If delta is small, it means that this interval kind of has to be small. But if delta is big, it means that the interval could be a bit bigger and we're a bit more relaxed. So this is an example where it's delta fine. This is an example where it's not delta fine. So suppose you have ui minus 1 and ui, and here we have ti. Then, in this case, suppose gamma of ti is very small. Then the problem is this ball doesn't contain the whole interval. The interval is kind of bigger than that ball. So, basically, delta fine really means small, but smallness is dictated by this gauge, delta. So, and here's the definition. If basically ui minus 1 ui is contained in the ball centered at ti and delta ti. So if delta is small, it means we're more restrictive, and I think that's usually when there's a singularity, we want to be super strict, but if delta is big, we're more relaxed. And in particular, there's a lot of flexibility in choosing our mesh. Whereas for Riemann, there's not much flexibility. It has to be constant, and there's a problem. All right, then, what is the gauge integral? Basically, what we want is, for every small mesh, this gauge sum should converge to something. which is precisely the gauge integral. And I'll give you an example in a second. So definition. I, which is denoted by the gauge integral, so I like to call it f of, so integral from a to b, f of x, and then usually it's dx, but let's call it delta x, or if you want d delta x, maybe that's better. This thing, we call this the gauge integral if and only if for every error, so for epsilon. So an epsilon is again the distance, if you want, between this integral and the gauge sum. So no matter how small the error is, we can always find some gauge. So there is some very good gauge such that for every small mesh, we do have that the distance between this sum and our integral is very small, such that if P is delta fine, so think small, but in terms of our gauge, then the difference between the gauge sum and our integral is less than epsilon. So essentially what you're saying is that the limit of this gauge sum of the sum of G is equal to our gauge function. And the sum really means if the partitions are sort of small enough, and again here smallness is in terms of that gauge function. Okay, so in other words, for every small gauge partition, this sum is roughly equal to a fixed number, which doesn't depend on the partition at all. So now let me give you two examples, because when I saw this, I was like, what is going on? But I think with an example, this might become slightly clearer. So first of all, let me show you that Riemann integrable functions have to be gauge integrable. And the gauge here is simply the constant one. So for example, let's talk about Riemann integrals. Then we get the following. Example, Riemann integration corresponds to simply choosing the mesh, delta is b minus a over n. Because notice, if n is big enough, then every partition is delta adapted. Because look, suppose you, again, suppose you subdivide your interval here in the Riemann sense into bunch of points, un, right, where in this case ui is a plus I b minus a over n. Then if you pick any point in that subinterval, so say ui minus 1 ui, and you pick your ti, well look, any arbitrary point here will be in your interval if the radius is b minus a over n. So we do have, if you want, ti, if you take the ball of radius, ti and delta ti, which is b of ti, b minus a over n. Well, by definition, it'll always be, that ball will always include your interval. Even if you take, let's say, the leftmost interval, then it's still okay. It still includes the ui minus 1 and ui. And so in particular, what does Riemann integration say? It says, in fact, for all epsilon, to show its gauge integrable, we just have to show that there is some gauge, which here is just b minus a over n, if n is large enough. Okay. And again, that's just for Riemann integrable. Then, if delta is this gauge, b minus a over n, the constant gauge, I get the function that's constantly equal to b minus a over n if t is delta phi. And in this case, all it means is that if n is large enough, okay, and because if n is large enough, any Riemann integrable partition is still still gauge fine, okay. If p is delta fine, then if you take that sum, so sum from I from 1 to n of f of ti, and then the length here is b minus a over n. If you subtract it from the Riemann integral, is less than epsilon. And this thing, it's, in other words, the if the f is Riemann integrable, then the Riemann integral corresponds to the gauge integral. So they're kind of the same definition here, but the point is, the gauge integral, because we have this delta, we have more choices of our meshes. And in particular, it's not surprising that, there are some gauge integrable functions that are not Riemann integrable. Because Riemann integrable has a very big restriction on the size of your partition, but the gauge integral is like, oh, let's not worry about it. Let's have some fun. And so, what I want to show you now is an example that illustrates this definition. And for example, let's pick a function that's not Riemann integrable, and let's see what happens. And in fact, let's pick the classical Lebesgue integrable function, which is the one that's 0 on irrational numbers and 1 on rational numbers. So let f of x be 0 on irrational numbers and 1 on rational numbers. And let's say on the interval 0, 1. So it's basically the function that's like 0 on a bunch of points, but then just 1 at some rational numbers. And as expected, the integral of this should be 0, because there are a lot of more irrational points than rational points. So claim, I want to say claim, like the like the gauge integral. I'm claiming that the integral of from 0 to 1 of f of x, and then and that's not right, delta x, that's right, d delta x. I think that's better. I'm claiming that the gauge integral is equal to 0. So what do we have to show? In other words, given an error, we have to show that you can find some tolerance, some gauge, such that for every acceptable partitions, the difference between this and 0 is less than your error. So let epsilon be given. And first of all, find delta, our gauge. So usually delta is a number, here it's a function, and here's how we're gonna do this. Because it turns out this is kind of bad at rational, I guess this is good at rational numbers, because it's 1 bad at irrational numbers, or vice versa, depending on how you see it. So let Rk, the rational numbers are countable. So let's just choose an enumeration of the rational numbers, like R1, R2, might be R3 here, and then R4, R5, R6. So let Rk be an enumeration of the rational numbers. And you'll see in a second why this is important. Because basically what we would like to do on each rational number, we would like to define delta. And in some sense, the more rational numbers you pick, the smaller it is. So in other words, define delta as follows. Which basically says, so on rational numbers, be pretty strict. On irrational numbers, be really relaxed, because it's 1 on rational numbers, so it's not 0, we have to be strict, else it's 0, so we can be more relaxed. So let delta, define delta by delta rk. So on the kth rational number, it's epsilon of 2 to the k plus 1, and else it's 1, if x not rational. So in other words, at irrational numbers, the radius can be very big, and we're more relaxed in this case. We're allowing for more coarser partitions, if you want. And now, so this is our gauge, and assume we have an acceptable partition. So if P, and again, we need all the numbers, so not only U0, U1 up to Un, but also our points T1 up to Tn. And suppose this is delta phi. And let us show that using this partition, the gauge sum is less than epsilon. So show the gauge sum of F is less than epsilon. Okay, let's see how to show this. So by definition, this gauge sum is just the sum from 1 to infinity, from 1 to n. So again, we have our ui, so this is 0, this is 1. Let's say u0, u1, un, and our points t1, t2, up to tn. So this equals to the sum of f of ti of the length of our partition. Now, remember the definition. The definition is f is 0 on the irrational numbers and 1 on the rational numbers. So, in particular, if f is 0, we can just ignore it from the sum. So it's really equal to the sum from I from 1 to n, where ti is rational, of 1 times delta ui, which becomes delta ui. So all that we need to show, if ti is rational, this thing is very small. But that's not a problem, because remember, our gauge was very strict at rational numbers. So we're kind of punishing rational numbers here. And in particular, because this thing is acceptable, because P is delta phi, what do we know? We know that if you have Ti and take the radius delta Ti, your interval, it's less than the ball here. So it's included in that ball. And so in particular, this ui minus 1, comma ui, it's included in the ball, centered at Ti and delta Ti. And what does that mean? In particular, the size of this, which is delta ui, is less than or equal to, well, here's a one-dimensional ball, so it's just twice times the radius, so 2 times delta Ti, or delta Ti plus delta Ti, but which is less than the radius of the ball. And then remember, we chose delta to be epsilon over 2 to the something, so it's 2 times epsilon over 2 to the n plus 1. We don't know what n is, so it's epsilon over 2 to the n. So each each length is less or equal to epsilon over 2 to the something. And here's the thing, if we chose the mesh to be uniform, then we might be in trouble, because if you add a bunch of fixed constants times epsilon, you might get infinity. But remember here, at every point we became stricter and stricter and stricter. So worst case scenario, this could be m equals 1. So worst case scenario would be epsilon over 2. Second worst case scenario, epsilon over 2 squared. And last worst case scenario would be epsilon over 2 to the n, which then becomes, oh, I already wrote that down, but that epsilon of 1/2 plus 1/4 plus dot 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 plus 1 over 2 to the n. But this is less or equal to the series, I guess strictly less, in fact, to the series 1/2 plus 1/4 plus dot dot dot. But that's a geometric series which equals to epsilon. So indeed, this thing, minus 0 is less than epsilon, and since this is positive, it's greater than or equal to 0. So, in particular, we have shown that the gauge integral is less. So, this minus 0 is less than epsilon. So, the gauge integral of f equals 0. So even though this function is not Riemann integrable, it is gauge integrable. And the cool thing is, it's even, well, it is also Lebesgue integrable. So somehow Lebesgue integrals are also part of this. But there are some functions that are not Lebesgue integrable, but that are gauge integrable. And let me finish off with this. So just a couple of cool facts. That's why it's kind of the best integral, because it sort of includes all the other ones. So cool facts. So Riemann integrable implies gauge integrable, and Lebesgue integrable implies gauge integrable. So in fact, it's the integral that includes all other integrals, because you see, here we have the Riemann integral. And basically Lebesgue is better than that, but there are some Lebesgue integrable functions that are not, some Riemann integrable functions that are not Lebesgue integrable functions, and those are the improper integrals. Improper Riemann integrals. And there are gauge integrable functions that are neither of the two. And I think, for example, we have this Fresnel integral, sine of x dx, sine of x over x. And I'll talk about this in a second. And but one cool thing though, even though Lebesgue integrals, they don't have a fundamental theorem of calculus, for gauge integrable functions, we have a nice one. Namely, the integral from a to b, if f is differentiable, then it's equal to f of b minus f of a. And the reason this is true, surprisingly, it uses my cool proof of the fundamental theorem of calculus that uses the mean value theorem. And it turns out there is some kind of mean value theorem for the gauge integral. Lastly, I want to finish up with the example I started at the very beginning. The, let's call this, the 1 over x sine of 1 over x cubed. So how can we find the gauge integral of that? Well, kind of using this fundamental theorem of calculus, I don't know how exciting this is or not, but it is true mathematically. So if you define f of x to be, I think, the gauge integral from 0 to 1 over x cubed of sine of t dt over t dt, and pi over 2 everywhere else. So if, I guess, x is not equal to 0. Sorry, it's the gauge integral, so that's very important. So this turns out we can find the gauge integral of that, which is just a Fresnel integral. So if you define f of x to be this antiderivative, then using the chain loop, what do you get? F prime of x equals the derivative of that, so minus 3 over x to the 4th, then sine of 1 over x cubed over 1 over x cubed, which then becomes really minus 3 over x sine of 1 over x cubed dx, I guess. No, this thing. Okay, then it's if f(x) is not equal 0, and then similar, I guess, from something like pi over 2 or something. If x equals 0, yeah, indeed, pi over 2. It's just using the definition of the derivative. And in particular, once we have that, this thing becomes, so we get precisely our function, by the way. So this then becomes the integral from 0 to 1 of minus 1/3 f prime of x, gauge function at x, and this then becomes minus 1/3 f of 1 minus f of 0, which becomes minus 1/3. So f of 1, it's the integral from 0 to 1 of sine of, oh, we don't even need that, actually. I don't know what I wrote there. This is the derivative, and it becomes the integral of sine of t over t, I guess d, the gauge integral of t, minus the integral basically from 0 to infinity, more or less, of this thing, which is, it is improper Riemann integrable, and therefore gauge integrable, and the value then is precisely pi over 2. And therefore what you get is simply pi over 6 minus that gauge integral, delta of t, and then so minus 1/3. Yeah. And then, well, that's all we can really say about this. And it turns out if you want, because this gauge integral exists, we can find some numerical value, so you get something like 0.208 or something. So it is interesting. It's a function that's not Lebesgue integrable, not Riemann integrable, but we can calculate the gauge integral using this. I don't know if that's 100% legit or not. I think it's a lot of fun. And finally, I would like to thank, let's see, what was it? Boming Jia, because I got the notes from him on his website and I thought it was really cool. So I hope you like this gauge integral extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.